everyone. Today let's start exercise 1.1 in real numbers. The first sum in exercise 1.1 is use Euclid's division lemma to find HCF of 900 and 270. Let's do the sum. We need to take first the division lemma. First, we should do the long division method of HCF in rough work. Let's take 273 273 it's 810. It became so smaller. Let's take 274 274 it's becoming 1080. It's so much bigger. So let's take 273 it's 810. 900 minus 810 is 90. Now let's take this 270 as dividend. 93 is 270. Now we got the remainder as 0. So the 90 is the HCF of 900 and 270. Now let's write this in Euclid's division lemma's formula. 900 is equal to 270 into 3 plus 90. Now we should take 270 as A. 270 is equal to 90 into 3 plus 0. We got the remainder as 0. So 90 is the HCF. This is the symbol of therefore. Now let's see the second sum in first Roman. The second sum in first Roman is 196 and 38220. Now let's do this sum. Again, first we should take the division lemma. Again, we need to draw a rough box. We take 196 as divisor and 38,220 as dividend. Let's take 196 ones are 196. 2 minus 6 cannot be possible, so we need to do borrowing subtraction. 8 will become 7 and 2 will become 12. 12 minus 6 is 6. Again we need to do borrow. 3 will become 2, 7 will become 17. 17 minus 9 is 8. 2 minus 1 is 1. Now let's bring the 2 down. Now let's do 196 nines. 196 nines is 1764. Again we need to do borrowing. 6 will become 5 and 2 will become 12. 12 minus 4 is 8. Again 8 will become 7 and 5 will become 15. 15 minus 6 is 9. 7 minus 7 is 0. 1 minus 1 is 0. Now bring this 0 down. And 980 is multiple in 196 table by 5 are. 196 5 are is 980. We get the remainder 0. So the 196 is the HCF of 196 and 3800 and 38,220. Now let's write this in division lemma's formula. 38220 is equal to 196 into 195 plus 0. We get the remainder 0. So 196 is the HCF of 38220 and 196. HCF is 196. Now let's do the third sum in first problem. The third sum in first problem is 1651 and 2032. First of all, we need to take division lemma. Again, we need to draw a rough box. We need to take 1651 as divisor and 2032 as dividend. We need to take the larger number as dividend always, and the smaller number should be divisor always. Now let's try 1651 ones are. 2 minus 1 is 1. 3 minus 5 is not possible. Even 0 cannot borrow. So 2 will become 1 and 0 will become 10 and then 9 and 3 will become 13. 13 minus 5 is 8. 9 minus 6 is 3. 1 minus 1 is 0. Now let's take 1651 as dividend. In 381 table, 1651 is not cancelled. So let's try 381 4s. 381 4s is 1524. We cannot do 1 minus 4, so let's do borrowing. 11 minus 4 is 7. 4 minus 2 is 2. 6 minus 5 is 1. 1 minus 1 is 0. Now let's take 381 as dividend. In 127 table, 381 is exactly cancelled in multiple 3. 127 3s is 381. We will get the remainder as 0. So the HCF is 127. Now let's write this in division lemma formula. 2032 is equal to 1651 into 1 plus 381. 1651 is equal to 381 into 4 plus 127. 381 is equal to 127 into 3 plus 0. We get the remainder as 0. So 127 is the HCF. Let's do an extra sum. 96 and 672. First of all, let's write division lemma. Again, we need to draw a rough box. We need to take 672 as dividend and 96 as divisor. In 96 table, 7s is multiplied, we get 672. 96 sevens are 672. So the HCF is 96. Let's write this in division lemma formula. 672 is equal to 96 into 7 plus 0. As the remainder is 0, the HCF is 96. Now let's do the second sum. In this, they ask to use the Euclid's division lemma to show that any positive odd integer is in the form of 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Let's take a as any positive odd integer. By using Euclid's division lemma, Euclid's division, A is equal to BQ plus R, where R is equal to or less than 0 and 0 is less than B. Now here it is given 6q plus 1 or 6q plus 3 or 6q plus 5. Here 6 is given as B. Let's take B is equal to 6. If B is equal to 6, then R is equal to 0, 1, 2, 3, 4 or 5. As here the R is given, it is equal or less than greater than 0 and less than B. Now if R is equal to 0, then A is equal to 6q plus 0, which is equal to 6q. Six is an even number, so even into any number is also an even number. So 6q is an even number. If R is equal to 1, A is equal to 6q plus 1. Here 6q plus 1 is an odd number because it is added with 1. If R is equal to 2, A is equal to 6q plus 2, which is an even number as 2 is an even number. If R is equal to 3, A is equal to 6q plus 3, which is an odd number. If R is equal to 4, A is equal to 6q plus 4. It is an even number as 4 is an even number. If R is equal to 5, A is equal to 6 cube plus 5. It is an odd number as 5 is an odd number. Here they ask that A should be any positive odd integer. Here 6q is positive and 6q plus 1 is also positive. Here all numbers are positive, but all are not odd numbers. Only 3 are odd numbers. So we take A is equal to 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. So we proved that A is in form of positive or odd integer where it satisfies the three rules 6q plus 1, 6q plus 3 and 6q plus 5. Hence, it's proved. Let's do the solution of third sum. The third sum is use Euclid's division lemma to show that the square of any positive integer is of the form of 3p or 3p plus 1. It is the same model of second sum. In second sum, we took a as any positive odd integer. Here we need to take a as positive integer. Now, by using Euclid's division lemma, A is equal to B cube plus R, where 0 is less than R and strictly less than B. Here B is equal to 3. So R is equal to 0, 1, 2. Now if we consider R as 0 or 1 or 2. If R is equal to 0, let's see what is the value of A. If R is equal to 0, A is equal to, so R is equal to 0, A is equal to 3q plus 0, where it is equal to 3q. As we need A as a square, we need to square on both sides. Square on A square is equal to 3q whole square. Here it is equal to 9q square. We can write 9q square as 3 into 3q square, where we take p is equal to 3q square, then 3 is equal to 3 into 3q square is equal to 3p. So we get the first rule. Now if R is equal to 1, then A is equal to 3q plus 1. Now we need to square on both sides. A square is equal to 3q plus 1 whole square. A square is equal to 3q whole square. Now we need to follow the formula. A plus b whole square is equal to a square plus 2ab plus b square. These are called algebraic identities. I kept more algebraic identities in the description. You can refer them. We need to learn all the algebraic identities to practice this lesson. Here A is equal to 3q. A square plus B 2ab. 2 3q into 1 plus B square. Here A square is equal to 9q square plus 2 3s are 6q. 6q 1s are 6q plus 1. Here A square is equal to 3. We can take a common 3. Here 3q square plus 2q plus 1. Here A square is equal to 3p plus 1, where p is equal to 3q square plus 2q. Now we are still left with one condition. It is if r equal to 2. If r equal to 2, a is equal to 3q plus 2. When we square on both sides, we get a square is equal to 3q plus 2. Again we have to apply the same formula. A plus b whole square is equal to a square plus 2ab plus b square. A square is equal to 3q whole square plus 2 3q into 2 plus 2 square. A square is equal to 9q square plus 12q plus 4. Here 2 3s are 6. 6 2s are 12. 12q. Now we can write this as a square is equal to 9q square plus 12q plus 3 plus 1. Now we can take 3 common. 3q square plus 4q square, 4q plus 1 plus 1. Now we can write this as a square is equal to 3p plus 1, where p is equal to 3q square plus 4q plus 1. Therefore, the square of any positive integer is the form of 3p, 3p plus 1. Hence proved. Now let's do the fourth sum. The fourth sum is use the Euclid's division lemma to show that the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8. Now let's do the sum. First of all, let's take a as an positive integer. Let's take a as any positive integer. Now by using Euclid's division lemma, a is equal to bq plus r, where 0 is less than or equal to r and r is strictly less than b. Now let's take b as 3. Let's take b is equal to 3. r is equal to 0, 1, 2 as r is less than b and equal to or greater than 0. If r is equal to 0, a is equal to 3q plus 0, which is equal to 3q. Cube on both sides. A cube is equal to 3q whole cube. A cube is equal to 27q cube. A cube is equal to 9 into 3q cube. It is equal to 9m, where m is equal to 3q cube. Now let's take if r is equal to 1. If r is equal to 1, a is equal to 3q plus 1. Cube on both sides. A cube is equal to 3q plus 1 whole cube, which is equal to 3q whole cube plus 1 cube plus 3 plus 3q plus, sorry, not plus, into 1 into 3q plus 1, as a plus b whole cube is equal to a cube plus b cube plus 3ab into a plus b. Now we need to simplify this. 27q cube plus 1 plus 9q into 3q plus 1. Then we get a cube is equal to 27q cube plus 27q square plus 9q plus 1. We get 27q cube as 27q cube as it is, and we get 27q square by multiplying 9q into 3q, and we get 9q by multiplying 9q into 1, and plus 1 is transferred to last. Now we can take 9 common. 3q cube plus 3q square plus 1q plus 1, which is equal to 9m plus 1, where m is equal to 3q cube plus 3q square plus q. Now if r is equal to 2, then a is equal to 3q plus 2. If you cube on both sides, a cube is equal to 3q plus 2 whole cube, which is equal to 3q whole cube plus 2 cube plus 3 into 3q into 2 into 3q plus 2. Now if we simplify this, we get 27q plus 8 plus 3 2s are 6, 6 3s are 18q into 3q plus 2. Now, if we simplify more, we get 27q cube plus 8 plus 54q square, as we multiply 13q into 3q, and 13q into 2 is 36q. Now we should take 9 common. If we take 9 common, we get 3q cube plus 6q square plus 4q plus 8, which is in form of 9m plus 8, where m is equal to 3q cube plus 6q square plus 4q. Therefore, the cube of any positive number is of the form of 9m, 9m plus 1, 9m plus 8. Sorry, not number, it is integer. Hence, it's proved. To the solution of fifth sum. Let's take n as any positive integer. Positive integer. By using Euclid's division lemma. A is equal to BQ plus R, where 0 is less than or equal to R and R is strictly less than B. Let's take B is equal to 3. So, R is equal to 0, 1 and 2. In case 1, if R is equal to 0, n is equal to 3q plus 0 divisible by 3. By 3. n plus 2 is equal to 3q plus 2. It is not divisible by 3. N plus 4 is equal to 3q plus 4. It is also not divisible by 3. Now case 2. If r is equal to 1, if r is equal to 1, n is equal to 3q plus 1 and n plus 2 is equal to 3q plus 2. Sorry, 3q plus 1 plus 2 and n plus 4 is equal to 3q plus 1 plus 4. 3q plus 1 plus 2 is equal to 3q plus 3 and 3q plus 1 plus 4 is equal to 3q plus 5. We get 3q plus 1 plus 2 as n is equal to 3q plus 1 and 3q plus 1 plus 2 is equal to 3q plus 3. So n is not divisible by 3. And n plus 2 is divisible by 3. N plus 4 is not divisible by 3. In case 3, r is equal to 2. If r is equal to 2, n is equal to 3q plus 2 and n plus 2 is equal to 3q plus 2 plus 2, which is equal to 3q plus 4. N plus 4 is equal to 3q plus 2 plus 4, which is equal to 3q plus 6. N is not divisible by 3. N plus 2 is also not divisible by 3. Where n plus 4 is divisible by 3. Here n plus 2 is divisible by 3 as 3 is divisible by 3, and here n plus 4 is divisible by 3 as 6 is divisible by 3, and here 3q is divisible by 3 as 3 can be divisible by 3. Therefore, one and only one out of n comma n plus 2 comma n plus 4 is divisible divisible by 3 where divisible by 3 in each case where n is an any positive integer. Hence, prove. I conclude this section with this fifth sum. In next section, let's start exercise 1.2. Now please subscribe, like, share, and also don't forget to press the bell icon beside of the subscribe to get the notifications of my videos. Also, please comment if any. Don't forget to comment if you have any doubts. Thank you.